A bit louder than I expected. Well, good evening, everyone. I hope you can hear me okay. Hello, Lex. Good to see you. Oh, I haven't done a mic check. Can you hear me okay out there on the internet? If this is your first time tuning in to Physics with Keith, hello. It is 6 o'clock. It is... Thank you, Edward. Am I actually muted? If I'm actually muted, then I'll have to try and figure out why that is, Pranav. Oh, never mind. Okay, super. Pranav, I think you're muted. Anyway, it's it's Tuesday. It's 6 p.m, so it's time for us to do some physics. Thanks, Pranav. As you can see, we've got some good interaction going on. If you see the chat on the right over here, if you're tuning in on YouTube and you don't know how to get to that chat, then all you need to do is follow the link in the description of the video to the Discord channel on the Discord server, and then you can join in. Although you won't be able to join in today because you're too late. You need to join in and get pre-approved before you can participate. It's easy to do. Follow the instructions on Discord and it'll be fine. We've had a week off, so I'm interested to see how many people join us because I have not widely advertised this today, so I'm interested to see how many people join us as we delve into the world of diodes. Yes, that's right, Edward. We have 700 subscribers, 300 left, and then I can embed the YouTube live stream onto my website, which I've just paid to renew. It cost me £51. Anyway, don't worry about that. So I can get the YouTube stream onto my website, and I can then hopefully, I figured out once, I'll be able to do it again, figure out how to get the Discord chat onto the same place. So everything on one website. That's what I'm hoping to do. We'll see. Okay, let's get on with this then. So, oh yes, I've got that loaded up. No, we'll come back to that later. Diodes. I want to show you about diodes. So let's start with what diodes do. Then we'll talk about the characteristics of diodes. And then I've got some questions for you, which start in a quite straightforward way, a bit of GCSE level, then they go a step further into A level. But don't worry, if you're a GCSE student and you're watching, I'll let you know when we make that transition. So let's start with what we can do with diodes. You can see here I have on the left something labeled input. This is a simulation from Dr. John Nunn. This is a virtual physics lab simulation, courtesy of the National Physical Laboratory. They very kindly gave me permission to use these simulations. I say that every time I use them. They've kindly given me permission as long as I tell people that, firstly, they are the NPL VP Lab simulations, and secondly, tell people they should go to that website and check out this resource. Just Google VP Lab, you'll find it. So this one here is for what diodes do. And on the left here, you can see we've got what's labeled input. And this is a supply where the potential difference from some sort of live connection is going from being positive, maximum of positive 3 volts, to negative 3 volts. Does anyone out there know what we call this sort of supply where there's a potential difference between a live wire and a neutral wire, which is oscillating from being positive to negative to positive to negative? Yeah, Noam has got it. Hello, Noam. Good to see you. AC, which of course stands for air conditioning. Alternating. Oh, that makes more sense. Yeah, AC. Hi, sir. Okay, hi. Yeah, alternating current. Yeah, so the supply here is an alternating supply. And if you connect a resistor across this alternating supply, then you'll have alternating current. This isn't the current supply, this is a potential difference supply. So of course, I could have 2 wires connected to my potential difference supply that are not completing a circuit, and the potential difference will be alternating, but there'll be no current. So AC perhaps is the wrong name for it, but that's what everyone calls it, so who am I to argue? This is AC, alternating current. Okay, so I can change what that voltage is, but I'm not going to bother. I'm quite happy with that being 3 volts. On the right-hand side over here is what's labelled output. So can I only use diodes in alternating currents? No, not at all. You can use diodes all over the place, Jammy. They are incredibly useful components. But I'm going to introduce diodes in this context because it makes it really clear what they do. And then I might talk about some of the other contexts where you'd use diodes later on. So here I've got the output. And what does this mean? Well, if you look in the middle, we've got a circuit diagram. We've got a power supply on the left here. And on the right-hand side, we've got what's coming out. Eventually, we've put a voltmeter across this supply here. And there's nothing in between. It's just two wires. And so, as you might expect, what we get out from this voltmeter here is what we put in, which is the supply. Incidentally, anyone know what we call a voltmeter, which produces a trace like this, where it's got a sort of a time axis? A voltmeter that produces a graph of voltage versus time. GCSE students, you do need to know this component as well. Although you probably won't learn about this component in the context of circuits. Yep, Noma's got it. It's an oscilloscope. It's a travesty, but you usually only meet oscilloscopes in GCSE level when you start looking at waves. Ah, hello, 𝘭𝘪𝘯𝘬𝘴. It's good to see you there. Yeah, usually people only start talking about oscilloscopes. Teachers only show oscilloscopes when they do waves, maybe a bit of maybe a bit of electromagnetism. But really, I think you should start talking about oscilloscopes very early on when you're looking at power supplies and potential differences in currents and things, because I think they're very useful components. An oscilloscope is a voltmeter, but it's a voltmeter that produces a graph with time on the x-axis and voltage on the y-axis. And so in the middle is 0 volts. So essentially what I've got here is an oscilloscope on the right and a power supply on the left. Okay, let's add a diode and let's watch what happens. Okay. I can see that someone's typing, so I won't say anything just yet. I will say something. I'll carry on talking. I love talking. I've added a diode. That's one of the acceptable symbols for a diode. There are others. They're all variations on this theme. Some have a circle around them. There are some diodes, Jammy, which emit light. We call those light-emitting diodes, or LEDs. And their operating principle isn't really any different to the principle of any other diode, except when the electrons cross the diode, they drop in energy and emit light. So that's more of an A-level thing there. So for year 12s and 13s, as the charges move across the diode, the energy level afterwards is lower than the energy level before, so a photon is emitted of a particular frequency. But that's more of an A-level thing. But yes, there are light-emitting diodes, Jammy. So we can see here that the top wire is the live wire. The bottom wire here is fixed at 0 volts. And so the top wire goes as high as positive 3 volts, as low as negative 3 volts, positive 3, negative 3, positive 3, negative 3. And yet this diode is doing something to the output trace. What's it doing to the output trace? I'll show you what it was like before again. So, not that one yet. This is what it was before. This is what it is now. Before, after, before, after, before, after. What's the diode done to the trace? Controlling it. It's a little bit vague. Limiting it. Yeah, I see words like that. Jammy, this is some good advice for you now. As an examiner, these are words I see quite often. Limiting, controlling. It's best to avoid words like that, which have a colloquial meaning everyone knows, but really there isn't a physics meaning to them. I like Edward's answer better. The voltage does not go below 0. Now, Jammy, I know that you can see that. I know that you've seen that. And in your mind, I suspect you're thinking, well, it is controlling it. It is limiting the voltage in the negative voltages. It is limiting them. Yeah, but this is language that an examiner can't interpret. So we need to be careful with our language, and we'll just describe what's happening. We still get the positive voltages, but now, as Edward said, we don't get any negative voltages. The voltage doesn't go to 0. There's a lovely word we can use for what happens when you cut something off. It does, Pranav, but we don't necessarily have any charge flowing. Okay? This is an alternating potential difference, and this is an oscilloscope. There isn't necessarily any charge flowing. So that's an A-level distinction. GCSE students, please don't worry too much about the distinction I just made for Pranav. That's just me having fun, but it is an important distinction. So, Jammy, it is correct that a diode... okay. The ideal diode doesn't have the 0.7 volt threshold, Pranav. Well, that's like slight knee. So, you get slightly different outputs from the ideal one to the real one. So, Jammy, so a diode prevents the flow of charge below zero. Again, the wording's a little bit difficult to pin down there. Diode prevents the flow of charge. I like that. In a particular direction, and that's in the negative direction, what we would call reverse bias. Reverse bias is the technical name for when we try to make charge go through the diode backwards, and the diode prevents the flow of charge in the reverse direction, backwards. The below zero part, well, below zero is the voltage, so the diode won't allow the voltage to go negative. So it won't allow the voltage to go below zero. So do you hear the difference there, Jammy? If we're talking about the flow of charge, if there's a circuit and we're talking about the flow of charge, then you're correct. The diode prevents the charge going backwards. If you're talking about the voltage, then the diode prevents the voltage going negative. So just be a bit careful whether we're talking about what the charges are doing, what the voltages are. So there we go. There's a diode. This on the right-hand side here, no worries at all. So this thing on the right-hand side here, how would we describe that, do you reckon? AC, DC? Any clever names you can use for it? Well, it's not a constant voltage, is it? Well, if it's connected in a circuit, then Jammy, you're absolutely correct. If this is connected in a circuit, then it is direct. It doesn't have to be a constant value. I wouldn't call it a pulse DC gnome, no. Mainly because I've never heard that terminology used. The word pulse does get used in the context of lasers, and pulsing a laser is a way of increasing the power of a laser. And that's the only time I can think of. Yeah, so the word pulse as a technical term in physics does exist, but I've never heard it used in this context. It's just direct current, but we can call this half-wave rectified direct current. So the clue is in the middle here. Half-wave rectified is because half of the wave is doing what it should do. It's rectified. It's doing what it should do. And the other half of the wave, well, that's gone. It's not alternating, Edward. It's definitely DC, because what makes something alternating is that the direction of the current changes. And you get a direction of the current changing if the sign on the potential difference changes. Not just the value, the sign. Positive to negative to positive to negative. In this case, it's positive to zero to positive to zero. So the charge wouldn't be flowing at a constant rate. It's not a constant current, but it's still always going in the same direction. Pulsing is a good colloquial word for what it's doing, Gnome. I like the word, but I wouldn't use that word in any sort of formal setting, because I think that would... It's not a technical term I've seen before. No, I would say half-wave rectified. Great, okay. So what's happening to the bottom part of the wave then? It's gone, but there was... You know, before there was a voltage there, and voltage is work done per unit charge. So there's energy there. And afterwards, the voltage is gone. That negative voltage is gone. So the energy's gone. So what's happened to that energy between the input and the output? I wonder what's happened to that energy. No one's typing an answer yet. Okay, a couple of people are typing. It's a good answer, Jammy. A very good answer. Can we take that a step further? In GCSE in particular, when we talk about energy, we always have to talk about what the store of energy is, how it's changing, where that store of energy is, and if we can, any forces that are involved. In this case, I wouldn't talk about forces here. So you've said, Gnome says the diode behaves as a resistor and dissipates the energy as heat. I like that. So can you see the difference, Jamie? In Gnome's answer, she said the diode behaves as a resistor, and it does. Do you happen to know, Gnome, what we assume the resistance is of the diode in reverse bias? And 𝗟𝗏𝗏 is typing an answer. That's a name I haven't seen before. Infinite, yeah. Of course, you can't have infinite resistance. Even air doesn't have infinite resistance. So we would just say it's incredibly high, very high, in the order of mega ohms, or even more than that. Yeah, so voltage divided by current is resistance, Jamie. Yeah, oh, Gnome's put it in quotes. Yeah, infinite resistance. So what we're saying is that for a particular voltage, let's just jump across to the whiteboard for a second. And let's get my pen out. What we're saying is, I'll write the equation Jamie's just told us there, which is absolutely correct. The resistance of a component is equal to the potential difference across the component divided by the current through the component. If R is really, 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 really big, then I is going to end up being really, 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 really small. It's fine, Jamie. Hey, listen, that's why we're doing this. So you say you haven't done this topic since year 9. What does the resistor do? The resistor dissipates energy. It takes a bite out of the available potential difference. So if I have a power supply, let's say a simple cell here, and a resistor here, like this, then what I've got, let's say this is a 6-volt supply. What this resistor does is it takes a bite out of that. And if there's only one resistor in that loop, it takes a 6-volt bite. If there are, in fact, two... I don't know why that's not working. If there are, in fact, two resistors, let's pop another resistor in here, like this, and they happen to be the same resistance to keep things simple, oh, that's badly drawn, then each takes a 3-volt bite out of the available 6 volts. That's what a resistor does. So the more resistance you have in your circuit, actually the less current will flow for a given potential difference. I suppose so. In series, yes, resistance will sort of split up that potential, and that's moving into something called a potential divider, which I do teach at GCSE level because it's useful to know about them. I don't think they're on the specification for GCSE level. They certainly are at year 12, and I do teach potential dividers to my GCSE students because I do think it helps. But another way of thinking about it is that the resistance is what's impeding that flow of charge. So the more resistance we have, the lower the current is going to be. That's what resistance does. And the way it does that is by taking more energy out of the charge. That's what resistance does. So as I go back to this picture here, if our resistance is approaching infinity, then the current approaches 0, regardless of what the voltage is, and that's how circuits work. I keep getting a warning coming up saying that my volume is too loud now. Is it? Am I distorting when I talk, or is it coming through okay? Because I've got my microphone a little bit further back, so it's not right in my face. Okay, that's good. I think it's okay. That's good. Okay, so we've got the we've got this this diode thing. Let's go back to this picture because I'm not done with this picture yet. Before I do some questions, where's my picture gone? Here's my picture. Not distorting or anything. That's absolutely brilliant. Thank you, Pranav. So that energy is being dissipated as heat, heating the surroundings, heating the diode. That's what it does. And if we've got a lot of heat, we'll have to dissipate that heat somehow by adding heat sinks to our component, things like that. And that's not very efficient, is it? In terms of energy efficiency, we're losing half the energy here. It's really not efficient. And yet the power that we get in our house through our plug hole is AC. No, AC averaging 230 volts. Yeah, Jammy, it's wasted. We're wasting half the energy. It doesn't seem very efficient at all. But there's a better design. And it's a bit of a tricky design to get your head around. Again, I do teach this to GCSE students. This is a bridge rectifier, as Gnome has correctly said, using 4 diodes. It is quite complicated. I will not go through now how a bridge rectifier works. I mean, I can do if you desperately want to, but you will not be, in your GCSE, asked about how a bridge rectifier works. A-level, you could be. So I will go through it if you want, but I don't think I really need to. No one wants me to. I'll wait. I'll tell you what, I'll put it to a vote. Let's see if I can do a poll here. How do I do polls again? Is it slash? I can't remember. It's been a while since I've done these. Create a poll. Yes? Question mark. And then choice A is yes. And choice B is no. Look at that. That is a poll if ever I saw one. A question is required. Okay, here's the question. If you could vote on that poll, whether you want to go through it or not, that would be helpful for me. Yeah, that's how it works. That's what happens, Edward. But the question is why? Wow. Okay, so it's pretty much unanimous that you want me to... Hey, that's all good. All good in the hood, as they say. Let's do it. Can't believe I just said that live to the nation. Okay, so let's start with our alternating supply. I'm going to go ahead and pop that right here. That's the usual symbol for an alternating supply. Here it is. I don't understand that notation. Does that mean I'm cool, or does that mean that I'm frozen right now? Should I be concerned? Okay. That's our alternating supply. Then what we're going to do is we're going to have that flowing into a diode, like this. And we're going to have that flowing into a... Oh, I tell you what, I like to give myself a bit more space there, actually. I'll give myself a little bit more space. Yeah, I'll give myself a little bit more space. I'll put the rectifier in first. Like this. And then I will... No, I've done something wrong. Let me go look at that diagram again. I can't remember why I can't remember it. Let's go look at that diagram again. Let's not be an idiot about this. We're live to the nation. Right, good. So we've got our supply, and we're going to first of all go into... let's take it on the left-hand side here. Let's go to there. And we go like this. There's our diode. Like this. Make sure I've got this right. And then that's going to go to an output like this. Just trying to draw it as I go along. There's going to be some sort of output resistor there. And that's going to come back in. It's going to be like that. That's going to be like that. And that's going to be like that. Think that's it. I think that's it. Right, let's see if that works. Let's see if that works. So let's run through this in 2 different directions. Let's start in the you can go away. Let's start in this direction there. So we've got current flowing in this direction here. So when I've got current flowing in this direction here, it goes along this wire here, down this wire here. Then it can't go down here because this diode is pointing in the wrong direction. So it goes up here. And then it can't go down here because this diode's pointing in the wrong direction. So it goes through here and it goes down here. And then that current comes along like this. Now it can't go this way. And the reason why it can't go this way is because this side is positive and we've just gone past this thing here. So now we're at 0 volts. So it can't flow that way. It just can't do that. It's in the wrong direction. So the current now has to flow up this way, like this. And then it's going to not flow here for the same reason. It can't flow that way because this is going to be positive. Now, this is the positive side of the resistor. This is the negative side. So instead it goes up like this. So there's the first route. And I'm going to delete all of those arrows. I'm just going to show that you're following the diode round. Let me get a highlighter pen out. You're following the diode. You can go away as well. You're following the diode around, the charge around. It goes this way. It goes up here. Then it has to go across here, down here, across here. It can't go up here, so it goes up here. And it can't go up there, so it goes up there. And that's the route that the charge takes when it's going left through the potential, through the supply. So now let's have it going right through the supply. And let's watch what happens. And I'll use a different color pen for this. So we had it going down like this before. Now let's follow it with a blue pen going in the opposite direction. So the charge is now flowing in the opposite direction. As that happens, it goes down here. It can't go up here. Yes, it can. It can go up here. It does go up there. It can't go down here. That's in reverse bias. It then comes along here like this. And will you look at that? It's going down here again. So that's positive. That's negative. Just as it was before. Now it gets to here. And it can't go this way for the same reason as before. If that's now positive and that's now negative, because we've switched it around, that's positive here. This is 0. And you can't have the charge flowing in the wrong direction. So it goes this way instead. For the same reason, it can't go this way. So it goes up. And it goes like this. So you end up with a charge, no matter what the direction is of the charge flow through the power supply, it's going downwards through the resistor each time. So again, using a highlighter pen, we go right, we go down. We can't go that way. It's the wrong direction. Charge goes this way, goes across here, down through here, across here. Can't go this way because it's going against the potential difference. So we go this way. Can't go that way for the same reason. So it goes up and across. So you have those two different routes. In fact, I might even use two different color pens to indicate those two different routes. Up there, down, up there, and then up there. There we go. So that's how a bridge rectifier works. Yeah, exactly. So when there's no potential difference, being able to follow it around is A level. So when there's no potential difference here, there's no potential difference here. When the potential difference here is in this direction, one color pen. When the potential difference here is in this direction, it ends up being in this direction. When the potential difference is in fact in that direction, it ends up being, would you believe it, in the same direction. And you can follow that charge around. And it does make a lot of sense. When the potential difference is 0 across the supply, the potential difference across the resistor is 0. I hope so. I hope so. So, but thank you, Edward. So here we go. We're going to get that little simulation out again. That's the bridge rectifier. That's what it's doing. It's not wasting energy anymore, which is good news. But it's still quite bumpy. And so just before we move on to some GCSE questions about this, and if you've got any questions, please put them in the chat. Oh yeah, Jammy. So can you become more than a regular? Can you become more than a regular? Jammy, I'm afraid I don't understand the question. Oh, yes. Yeah, so there are, yeah, you're talking about the different ranks on Discord. Yeah, so there is pre-approved, which is for people who have just joined but haven't actually. Yeah, I got it, Finadip. Thank you. Yeah, I got it now. Yeah, so there's pre-approved for people that haven't made it clear that they're not just trolling. That's all that's for. Then you go on to the approved, so participant. Once you've participated a few times, then I switch you across to a regular and you get access to all those resources. And really that's it. There is another role. You'll see some people's names appear in green, like Pranav and Wombat, and there are a few others whose names appear in green. They're moderators, and that's because although everything I do on Discord is public, there are various bits that aren't. For example, if someone deletes messages, or if I have to contact someone directly about an issue, a trolling issue, then I need to cover my own back. So moderators are there to help me with that, to delete inappropriate content when I'm not watching it at all times. That's me. The role titled Keith is me, and obviously I have access to everything on this server, and so there are different roles like that. But essentially, that's the role of the moderator. I give the moderator role to people I know and trust. And there are people who are over 18 who have had DBS checks done on them who have that role. And there are some students who I trust and know quite well who also have that role because they have a better insight into what newfangled slang language you young people use. So that's what the different roles are. Cool. Okay. Now this is Bumpy. Bumpy is fine for making a light bulb turn on. So Gnome, I know you're keen to say this, but we need to know what's the point of that. Why smooth down that potential difference at all? And for most components, you don't need to bother. But for sensitive components, you do. And by sensitive components, I mean electronic things. Sensitive sensors, for example, where if they've got an oscillating electric field nearby, it's going to mess up the reading. This has a heating effect as well, bouncing the electric field up and down. So what you can do is you can smooth it out, and you smooth it out by popping a capacitor in parallel with the power supply, and it smooths out that load. It's very clever. Essentially, you charge the capacitor, which is in parallel, so it doesn't affect the potential difference because we know about Kirchhoff's second law. It's in parallel. But then as the potential difference across the supply drops to zero again, the capacitor then discharges, providing that bit of potential difference across there. There's also circuits that have inductors to try to smooth out currents, but I'm not going to go into those. So that's diodes. Last thing about diodes then is what we call their characteristics. And this is GCSE level, very definitely GCSE level. A graph of characteristics is a technical name for a graph of the, let's get this like this, the current versus the potential difference. Hang on, my Google's just activated. I must have said something that sounded like, well, I won't say it. I will say it. Okay, Google. No, it's activated again. Leave me alone, Google. Okay, so a graph of current versus potential difference. You need to learn for GCSE level 3 different component characteristics graphs. The one for a fixed resistor, which is simply a straight line. A fixed resistor has a constant resistance. That means the resistance doesn't change when the voltage changes. The resistance, as you've correctly said, V equals IR. So the resistance is the voltage divided by the current. And if you look at this graph, at any point, voltage divided by the current is going to be the same. So that is the fixed resistor. You need to know the characteristics for a lamp as well, a filament lamp. On a filament lamp, you get something that looks a little bit like... Oh, that was terrible. What a terrible graph. You're supposed to have some sort of 180-degree rotational symmetry there. Essentially, it looks straight here, but then curves off at the end. And that's happening because the resistance is increasing at higher voltages. And that's because the lamp is getting hotter. So you need to know that. The last one is the diode. The diode is very clever. And at GCSE level, you learn the diode characteristics like this. It's zero current when it's negative voltages. So if you look at this axis, this graph, this is negative voltages. That's 0 volts. This is positive voltages. Thank you, Gnome. That's perfect. Absolutely perfect. Can always count on you. So we get this graph where they got the zero current and negative voltages. You then have to know that it's zero current up to a certain voltage. And it does depend on the diode. And if it's an LED, it changes what this value is again. But essentially, hopefully you can see that blue line. It's not too thin. But essentially, at a certain voltage, which for most silicon diodes we take as about 0.7 volts, all of a sudden we get a current flowing. And this part of the line here should be really, really steep because it's almost no resistance. It's not very visible. Right, let me do something about that, shall we? Let's click on this and let's go into pen properties. And let's fatten it up a bit. How about now? Hopefully that's better. Yeah, that'll do. So we've got essentially zero current. No, the current never goes negative. Look at that. There's never a negative current, ever. So all these negative currents down here just doesn't happen. You get zero current, zero current, zero current. And then about 0.7 volts, you get current. And this line should be nice and steep. Okay, remember that resistance is voltage divided by current. So if the current is very, 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 very small, the resistance is very, 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 very high. So this here is resistance approaching infinity. Very, very high resistance there. And this part here is a very, very low resistance. This is resistance approaching 0 at this point here. These arrows are getting confusing. There we are. Yes, that's not to scale that. And there's a problem with that graph, quite a big problem with that graph, Gnome. So where did you get that graph from? There's three big problems with that graph and counting. I'm not happy with that graph. There's 3 problems with that graph and counting. Google search, yeah. So let me just copy this image and I'll point out all the problems with this graph. No, that's not actually... Yeah, Gnome can guess a few things that I probably dislike. It's not actually the negative current that's a problem as such, 𝗵𝘳𝗶𝚳. So there's a few problems. The first one is it's nowhere near to scale. The breakdown voltage is around about negative 50 volts for a silicon diode, whereas we get this knee voltage at about 0.7 volts. So if you look at this scale, what is happening there? Negative 50 here. And yet, hello, something's vanished. Negative 50 volts here, but 0.7 volts there. I don't think so. That's bad. Second problem is this curve is far, far, far too gradual. Far too gradual. It is true that there is a teeny tiny negative current here and a teeny tiny positive current here, but you do see a very pronounced... Yeah, I'm not happy with that, Gnome. It's not a pronounced enough knee. You need a more pronounced knee. It's still not to scale. The other problem with this is that we've got an arrow pointing up and pointing down. An arrow on an axis points in the direction of positivity, the direction where it's getting more positive. So this makes no sense. The graph that I drew, where it had an arrow pointing up and an arrow pointing right, but no arrow pointing left or down, means that this is increasing positive in this direction. So this is negative, this is positive, and increasing positive in this direction. On this graph, I don't know what that means. I don't know who drew this, but it's not a good graph. That's much better. Edward, I like that one. Where did you get that one from? The other problem with this graph is that once you hit breakdown voltage, it's not a diode anymore. Edge. I don't know what that means. Once you've hit, is that the browser? I don't care about the browser. Once you hit the breakdown voltage and you get that breakdown of the diode, it's not a diode anymore. Yeah, but where did what website gave you that picture, I guess? Because right now I'm showing a picture. I don't know if that's under Creative Commons license or I've just broken copyright. There we are. I'm probably breaking copyright here. Oh no, I'm always so careful. Okay, so let's move on to some questions, shall we? Now that we know what a diode does, we've got a feel for what the diode does. We know how it's useful. Let's go and see how it plays out in real life. So, here's my question generator, which, if you're a regular participant, you are able to see these question generators on the Discord channel that's called Regular Participants. So if you have a look on the chat below, the chat's now vanished, but you'll just see file after file after file after file after file after file. You can search for what you want to find. It says it's from Bite Size. Yeah, that's definitely under copyright, Edward. Right. So if I go through this, what's below, it's all of those you can search for and you can download those if you're a regular participant. If you're not a regular participant, then you can't. You can still get them, but you have to pay for them. Or participate in Physics with Keith, and then you can get it for free. Those are the options. So this is one of them. This is my Kirchhoff's laws drill. And this one allows us to use diodes in our circuit. Now, this is a GCSE question. In fact, I don't like this question. I'm going to make it change it. You can change the question by hitting F9 on your keyboard. Okay, I'll stick with this question. So with this question, what I want to know is what the voltage is across these three components on the right and what the current is through the whole circuit. It depends on what order things are taught, Jammy. It's not quite as clear as that, whether it's the beginning or the end of GCSE. Because different teachers will teach in different orders, different schemes of work follow different orders. I tend to teach it in year 10. So I tend to teach it quite early on. Okay, so I'm going to give you one value to start with. The diode has 0.7 volts across it. And the second thing I'm going to tell you is that the diode is non-ohmic. That means you cannot use V equals IR on this component. It's non-ohmic. So with that information, can you compute what the voltage is across each of these components and what the current is through all of this? It's one big series circuit, so the current through all of this. Now, once you've worked it out, don't type the answer. I'm going to give you just a couple of moments to work it out. But don't type the answers. And then I'll pick a component at random and I'll ask you what the voltage is across it. And we'll see who gets the answer. It's not so much that, Jammy. It's you cannot use that equation at all. Yes, Edward. The voltage across the diode, don't forget the units, 0.7 volts. Can I give you a hint? Point number one, use Kirchhoff's second law, which we covered last fortnight ago in the last session. If you can't remember Kirchhoff's second law, it's that all of the voltage you gain, you lose within a loop. So see if that helps you. So don't type your answers yet. I'm going to give you a few more moments. So, Blah, I see your question. And the answer is no, it is not. If you connect a diode across a 0.3 volt power supply, then it will have 0.3 volts across the diode. If you connect a diode with nothing else, just a diode, across a 10 volt power supply, it will have 10 volts across the diode. If you do that, the diode will explode. It will go bang, you'll see a puff of smoke, I'm not exaggerating. You'll make a bang, you'll smell it, it'll make a puff of smoke come out of the diode, and you will have broken the diode. Because it's essentially got zero resistance, and so the current goes really high, and it melts the components in the diode. So what you need to do whenever you use a diode is make sure you've got a safety resistor, at least one. In this circuit, we've got 2 resistors. And whenever you've got a resistor, then you could get a variation. You could get more than 0.7 volts. You could be less than 0.7 volts, but not by a lot. It's going to be around about that number. And this goes back to that simulation. I think it was Pranav said, how's an ideal diode different from a real one? Well, a real one, there's going to be some variation. And it is a fiendishly difficult thing to solve questions with diodes in it where you don't take the diode as being an ideal component. When I say fiendishly difficult, I mean it is the first time you'll use calculus when you're at university to solve a circuits problem. A-level students know what calculus is. You've met it in the context of mechanics. The idea of using calculus for a circuits problem probably seems a bit alien. Don't give me the answers yet, Edward. Oh, what's happening? Everyone's giving me the answers. All right, I guess you might as well give me the answers then. Right, so... okay. But you've given me the answers now. So this is the first step. Yeah, good stuff. This is the first step. The first step is to figure out what the potential difference is across these 2 resistors. That's the first step. What's the potential difference across these 2 resistors? So between this point here and this point here, let's imagine we've just bunged a voltmeter in here. And the potential difference across those 2 is going to be this potential difference, which is 9 volts, subtract this potential difference. So that's going to be 9 subtract 0.7. I'm no mathematician, but I make that 8.3 volts. And then you can work out what the combined resistance is here. If you want to really, go over the top with this, these 2 resistors could be replaced with a single resistor that does the same job, does 160 ohms of resistance. Okay, let's take it a step back. Yeah, let's get rid of that bit there then. What shall I do? Shall I put step A like that? That's probably a bit better, isn't it? Yeah. Pranav, exactly as predicted. Yeah. Yeah. Yeah, way better. Good. So, Jam, are you still lost or are you okay now? Now you're good, okay? So stage A, part A, is calculate the voltage across these 2. Part B, if you really want to stretch it out, is, well, what's the resistance between these 2? So we do our 80 plus 80, and that's going to be equal to 160 ohms. I haven't got enough room on the side of the screen. I might just have enough room to squeeze a unit in. Yeah, it just about fits. Fine. So now what I've got is a voltage between 2 points and a resistance between 2 points. And these 2 points, everything here is ohmic, which means that for part C, I can use V equals IR rearranged. So divide through by R to get I equals V over R. I can use that equation to compute what the current has to be. So the current is going to be 8.3 divided by 160. And if I do that, I get, Noam says 52 milliamps, which disagrees with what Edward said, which is interesting. So let me see what I get. Yeah, I have to agree with Noam. Ah, yeah. Yeah. Pranav, how did you get that? I'm interested to see. Oh, okay, typo. Fair enough. Okay, so we've got our current now, which is our 52 milliamps. Or if you prefer to write it out like that, that's absolutely fine. That's in amps. I've written the amps, but you can't see it because it's off the side of the screen. So now what we're going to do is use that current. You don't need the imaginary double resistor now. We don't need that. We don't need this voltage between these two anymore. We don't need that. Because now what we know is the current through here is 0.052 amperes. And that's the same current through all of these. So we can now use V equals IR here, 80 multiplied by this, and V equals IR here, 80 multiplied by this current. So 80 multiplied by that current. Use the unrounded current that's probably still in your calculator. And you get, as predicted, 4.15 volts. And you'll get 4.15 volts here as well. And that's it. That's the question done. So it's not too bad. It really is just GCSE level. There is a quicker way, of course. Anyone want to tell me what the quicker way is? This is a nice formulaic way, which can't go wrong. Anyone know what the quicker way is? So, Blah, you're talking about the quicker way. That's good. Can't I just have halved the 8.3 volts? But why? Why can I just halve the 8.3 volts? There's something special about this circuit that means I can. Yes, no. They are identical resistance. Well done, you. Because they're identical resistors, it's a potential divider. You see, this is why I teach potential dividers to GCSE students. It's a potential divider, which means that and because of the same resistance, they get the same share of the voltage. You know that they have the same resistance, so they have the same voltage. Yeah, so they get the same share of those 8.3 volts. So it's a nice question. Let's try another one. Why am I rubbing it out? I might as well leave it there. Let's try another one. Oh, by the way, on these drill spreadsheets, when you click answers, you get the answers. There we are, 52 milliamps, thereabouts. And if I scroll all the way down to, scroll up to the voltage there, 4.15 volts. And we're always going to have diodes in these drills as 0.7 volts that the knee happens. And at GCSE level, you do really need to know that. Okay, so here we go. I know this bit on the left looks complicated, but I want to keep it anyway. You know this is just 6 volts. 2 cells in parallel is still going to be 6 volts. So this is 6 volts over here on the left. And I want to know the current through and voltage across each component. But I don't want you to type the answer yet. I want to give people enough time to get the answer. Squeaky chair. I see Noam's typing. I hope she's not about to give me the answer. Oh, and Jammy. What's the voltage? Across the diode is 0.7 volts, Jammy. And across the supply, I know it's 2 in parallel, but it doesn't matter. It's 6 volts. 6 volts across the supply and 0.7 volts. Next session, next week, we're going to introduce the idea of internal resistance. That's for practical circuits. But for this week, we're still using our ideal components. Got another lamp under here as well. I've got my strip light across here, which I fitted, and I've also got this little lamp here. But it doesn't seem to have any impact on the clarity of my image. It just means that I get blinded by the light. It's not clearer with the lamp on than it is with the lamp off, is it? So what's the point of the lamp? I'll just leave it off. A colleague of mine let me use this camera. It's much better than the camera I had. I'm very, very, very pleased with it. I'm very grateful to that colleague. Okay, so let's start with the current. Let's do it that way around. If you could all type what you think the current is around this circuit. I suppose I better calculate what it is then. Oh, no. This is interesting. So I seem to have a different answer. Yeah, Pranav, that's what I got. I seem to have a different answer to Gnome, to Edward, and you two usually get this sort of thing right. A different answer to Jammy as well. And I wonder if it's because the layout of the circuit has changed slightly and it's tricked people. So there's an idea in circuit topography, which is that it doesn't really matter what order the components go in. The circuit rules... Oh, I've bunged that in the wrong place. Where have I just pasted that? Oh, well, never mind. The circuit rules work either way. So the fact there's a diode midway through doesn't really matter. Blar, I agree with you and Pranav. Where did the 11.3 volts come from? Because Kirchhoff's second law is that within a loop, what we gain, we lose in voltage. So here is one loop. There's one possible loop, because the cells are in parallel. And here's a second possible loop. There's a lot of chatter going on in the chat, which is brilliant. So can you see that it doesn't matter whether we go through the left-hand or the right-hand cell. This battery of cells has a potential difference across it. Platypus, for the purpose of GCSE and A-level, yes, they do. Pranav, absolutely. So Gnome forgot to remove the diode. Yeah. Jammy, that's fine. I mean, this is a note to everyone. You can watch old lessons. They're all still available on the website. I've just noticed the time. We are coming pretty much to the end now, which is a real shame because it's a fun question. But essentially, the rest is the same as what we've already done. You know the total resistance is 160 ohms. You know you've got 5.3 volts across those 160 ohms. You calculate the current, which as Noam has now calculated, as Pranav, as who else was it? 𝗏𝗂 correctly said, that was 0.033 amperes or 33 milliamps. Once you've got the current, you can then apply that to each of these resistors to compute the voltage across them. And if you do that, then you get these answers. So there's your voltages. And you can't just say, well, there's two resistors, so share the voltage, because it doesn't work that way. It's a potential divider, but the potential's being divided three ways. A three-way potential divider is still a potential divider. Or you can do it the way I've just showed. And there's the answer, so 33 and a bit milliamps. Okay. Well, that was diodes. They can be tricky. If you want some more help with the circuit rules, if we go into here, where you've got the previous one, circuit practice, click on the link here, it will take you to a YouTube video, the YouTube stream from last time, which was recorded. So you can watch that circuit practice one. I haven't stripped out the first 10 minutes yet. And you can see all the circuit rules explained here. You're very welcome, Jamie. Very welcome indeed. So that's all still there. We also have on the what's it called? The Physics with Keith website, all the links to all the things that are coming up later, and there's some other links up here if you want to look at any of them. And finally, Isaac Physics. I've set another homework for diodes. So if you are not on the Isaac Physics group, can I encourage you to get on the Isaac Physics group? I will paste a link into the Discord chat now. So there it is. That's the group code 𝗵𝗵𝗃𝗃. If you could click on that link, make sure you're in the Isaac Physics group, and then you'll get some tasks sent to you. For example, I've just made a board of questions about diodes. And on this diodes question board, it starts with GCSE questions. You can see here, Year 9 GCSE. So GCSE questions about diodes. First three are GCSE, then the first four are GCSE, then it gets a little bit more challenge as we get further up. With the last question, I would expect Year 13s to be able to do. GCSE students, have a go at it, but you need to know about capacitors, and I'm not sure you'll be able to do that. But do as much as you can. Hopefully that's been useful for you. I've been Keith. This has been Physics with Keith. I'll see you next week. Stay safe and tell all your friends about it and stuff. Okay. Bye then.